Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. And so far, we have looked at the basically explicit method for solving ordinary differential equations, such as Euler method, Runge-Kutta method. In all the explicit methods, we calculated we created an iteration step, an iteration sequence, and at each step we used the values x and y from the previous step to find the new value of the function. And the idea was that if a is the initial point and we know the value of the function at an initial point, then if we want to find the value of the function at another point, at a later point b, we just discretize the interval between a and b into n subintervals, and we start from the initial point and write down an explicit equation that gives the value of each of y at each of the subintervals based on the previous value. Okay, but implicit methods are not exactly like that. In implicit method, at each step we have to in fact solve an equation to find the value. So we end up with an implicit equation in terms of yn, xn, yn plus 1, and xn plus 1. And because we already know the value of the xn, yn, and xn plus 1, the only thing that remains to be found is yn plus 1. All right? Now, why do we even look at the implicit methods while we already have explicit methods? It's because of something called stability of differential equations, and explicit methods tend to become unstable for large intervals. And a measure of instability or a measure of stability is a test given by y prime equals ky with the initial condition of y of 0 is 1. Now, we said that in general our equation is always of the form y prime equals f of x and y. All right, now we can use different methods to solve the ODE. All right, so, and we said that in general for the equations that typically happen in nature, in systems that we deal with, exponential solutions are the fastest, have the fastest growth and decay rates. Okay, we typically don't get anything faster than exponentials. And this special ordinary differential equation y prime equals ky with y0 equals 1, all right, can have two types of solution, either an exponential growth e to the kx or an exponential decay e to the minus kx. All right, and if the numerical method ends up to have a good stable solution for this test ODE, then we say that it's a stable method for solving the ODE. And there are generally two types or two families of stability. The first one is astable, and we know that if k is negative, e to the ky, e to the kx goes to 0 as x goes to plus infinity. Now, if the numerical solution also behaves this way, if we use a uniform step size for solving the differential equation, if the numerical method also behaves like this, then we say that that particular method is astable. Now, L-stable is more like a stronger version of astable. So in general, we can assume astability means a weak stability and L-stability means a strong stability. L-stable means region of absolute convergence has on the complex plane contains the negative part of the real axis. All right, now what it means is you have to go actually look at the detailed descriptions of the stability to understand what this means, but I just put it here for your information, so you can just Google it or look at Wikipedia to get more information. All right, now the key point here is that explicit methods, for example explicit Euler method, which we also called it forward Euler method, are typically unstable. All right, and Euler method in particular is unconditionally unstable, so you cannot do anything about like basically regardless of what the basically there is no condition that you can put on the differential equation such that it becomes stable. And on the other hand, implicit Euler method, backward Euler method, is A stable and L stable, so it's both of them. And what this means is that then it's basically based on, if stability is a concern in our situation, then we have to consider something like an implicit Euler method instead of an explicit Euler method. All right. Now, as I mentioned, the problem with implicit method is that it doesn't give you a straightforward sequence for approximating YB based on the initial condition YA, because at each step you end up with an implicit equation. So what do I mean by that? So here in the Euler method, we said that y prime is f of x and y, right? So let's say at some point x with a step size h, we want to find the value of the y at x plus h. Now we know that y prime at x plus h is f of x and y, all right? Now for the forward method, we put here f of x and y of x, and we approximated y prime of x plus h with a simple forward approximation, forward difference, y of x plus h minus y of x over h, all right? Now we still do that here, but in the f function, instead of putting y of x, we put y at x plus h, all right? And then what happens is that then y of x plus h minus h times f of x, y x plus h becomes equal to y of x, all right? And now if we create our sequence yn that converges to the value of y at b, right, converges to the yb, starting from y of a, then we end up with, so yx is basically y of n, and a step size is h, and then basically, so if we want to find y of n based on previous step, xn minus 1 and yn minus 1, this is the equation, right? So y of x plus h is basically yn, which is unknown, minus h, f of x, h here is the step n minus 1, so it's xn minus 1, but then we have yn instead of y of n minus 1, right, equals yx, which is step n minus 1, yn minus 1, all right? So we're solving this, we're generating this sequence, and what we need to find here is yn, right? We already know xn minus 1, we already know yn minus 1, but we do not know yn. And in general, f of x and y could be a very complicated nonlinear function, right? So what happens here is that this becomes a very complicated equation, but we already know how to solve such an equation, right? We can use something like a bisection or Newton-Raphson method. So solving the equation in general is not a problem. But the problem here is that for bisection methods, for the method that require root bracketing, it's not easy to guess where exactly the yn is, right? It's not easy to base, because we really don't know the behavior of the function at any given point, so we don't know how to choose an initial bracket for the root, which is yn. That's why the Newton-Raphson method, which only requires a guess, it doesn't require an initial bracket for the root, are always preferred. And you always hear about NR iteration method. NR is Newton-Raphson. So most commercial softwares use NR iterations or Newton-Raphson because you only need an initial guess. And in most engineering and physics systems, the function doesn't have a rapid change, so you can in fact set the initial guess of the Newton-Raphson method to yn minus 1, right, the previous one, and that's how we're going to do it. So we already have a very good guess for yn, and it's just yn minus 1, and then we solve this equation, implicit equation, to find yn, all right? And this whole story about implicit equation is just because of the stability. And again, in most cases, we don't need to do this. We just use Runge-Kutta fourth order explicit or Fehlberg explicit, and we can solve the differential equation with a good accuracy and not worrying about the stability. Alright, so here's an example. So this is the code. Again, everything implementing implicit Euler method is very similar to the previous cases. We start with a sequence, with a method that generates a sequence that converges to the value of y at a later point. Starting from x0, we want to find the value of y, the solution at x1, right? Y of x1. So we create a sequence that converges to that. So this is a multi-line lambda expression. If n equals 0, we're still at the initial point, so y0. Else, we copy x0 and y0. H is our uniform step, so we always do uniform partitioning, right? I'm going to write it one more time here, but you already know it by now that we're doing uniform partitioning, which always preferred in the ODE methods, ODE solver methods. So h is x1 minus x0 divided by n. So we're dividing the region from x0 to x1 to into n subintervals. And then I create a real root function, right? Root equation. Our root equation is going to be this one. And then real root, which solves for the roots, root solver is originally initiated to null, all right? And we know that we always had this for loop that generates a yn from yn minus 1, right? So it goes all the way from y0 n times. We have a loop, n loops basically. The loop goes n times, and then it starts from y0, x0, and eventually it should give us yn and xn, all right? So what do we need to do here? I'm going to copy x and y, which is basically x0 and y0. And the reason I'm copying them because in this lambda we have to use, if I want to use them here in this lambda expression that defines the root function, root equation, I need to declare them as final. But then the problem is that x and y cannot be final because in each iteration of the loop they are incremented. So I increment x because x and y start from x0 and y0 and then become x1, y1, x2, and y2, etc. So I cannot declare them final because they're not constant. Therefore, I'm just copying them and then use the copied versions in this lambda expression. All right. Whenever you're trying to use a variable in a lambda expression, it should be defined as final outside the lambda expression. Otherwise the compiler complains about that. All right, so what is our root equation? Our root equation should be written for yn. So yn, let's call it z, it's the variable, and we know that in each step of this for loop x and y hold the values of the current step, which is xn minus 1 and yn minus 1. So my equation becomes z minus h times f of x and z equals y. All right, z minus h times find that value x copy and z minus y copy. All right, so this function becomes equal to 0, and remember z is the variable which is what we're solving for, which is yn, and in this for loop x and y are the values at each iteration. They're the values of the current step. So we start from x0, y0, solve this equation, and the root solver is basically a root finder with this root equation. And note that I'm using Newton's method, and as I said, we already have a very good guess for the solution, which is current yn, or it starts from y0. So we start from y0, the Newton solves it with 100 iterations, max 100 iterations, and gives us y1, and then x0 is incremented to x1. And then in the next loop, in the equation, we have x1 and y1, and then we solve with the initial value, initial guess of y1. We get y2, and then x is incremented from x1 to x2, and etc. So this for loop can correctly generate the sequence that we want by solving the implicit Euler equation, and after that everything else is the same. If I want to actually find the solution at x1, I call the sequence, I create my sequence that converges to the value of the solution at x1, and do a fourth order Richardson acceleration and evaluate it at some step of the sequence, let's say 100 terms into the sequence after fourth order Richardson acceleration. And as I mentioned, we typically use Newton-Raphson for finding the roots, and the reason we're doing that because then we don't need to hassle with looking at how to choose a root bracket, how to choose a bracket for the root, and the initial guess for yn plus 1 is just yn, and that makes life easy. All right, so here's an example. We had this before for the explicit Euler, now we compare it with the implicit Euler. So y prime equals negative y, and y of 0 is 1. And we already know the solution, which is e to the negative x. And on a log scale, this blue curve, which is a perfect line, is the exact solution. And this red one is the Euler method. Note that this Euler method doesn't have any, I didn't include the fourth order Richardson acceleration in this red one. All right. And then this green one is the implicit Euler without any fourth order Richardson acceleration. All right, so these are just the baseline Euler method, and they are evaluated, I believe, at 100 terms into the sequence. All right, now what you see is that the Euler method immediately diverges, so it doesn't really track the exact solution. The implicit Euler method, so the red one was the explicit, tends to stay closer, so it has a smaller error as we get away from the initial point, which is x equals 0, but at some point it flattens out, and this is due to the tolerance that we set for basically the tolerance that I set for solving for the root finder algorithm. We said that at some point we have to stop the iteration, right? These are all iterative methods, and that's based on the amount of absolute error that we want. And I said that here I probably set it to 10 to the negative 12 or something. So after that it just basically becomes flat. All right, so that could be a problem, but we already saw that Runge-Kutta method or Fehlberg method, they can give us very accurate result without doing any implicit calculations. So as I mentioned, the Runge-Kutta method or Fehlberg method, fourth or fifth order errors, method that have fourth order or fifth order errors are typically good, the explicit ones, but they require more calculations of the function. And if we have many equations to be solved, then Euler method is still sometimes or most of the time Euler method becomes the preferred choice, and due to the instability of the explicit Euler method, implicit Euler method is usually preferred. All right, so implicit for a big system of equations, let's say 100 equations, probably using a fourth order Runge-Kutta is not a good idea. So just the implicit Euler method plus a Newton-Raphson iteration might be a better idea. Okay, now the question is, how do you actually apply this to a system of equations? Because dealing with a system of equations is not basically easy, and the reason is that in order to solve a nonlinear system of equations, the Newton-Raphson method becomes complicated. You have to calculate a special matrix, and that's not easy, so it becomes complicated. But for a single ODE, we can use this implicit approach. All right, so let's head to Eclipse and let's quickly have a look at the code. So here I have a test Euler implicit class, right? And I have two tests. Test 1 is basically what I just discussed. I'm setting a timer, and then drift function is x and y goes to minus y, so I'm solving y prime equals negative y. I create my ODE solver passing the function x0, initial value of x, initial value of y. So I'm solving for y0 equals 1. And then I create my Euler implicit sequence for x equals 0.5. So we're looking for y of 0.5. And then 100 indices, y and vals. These are the values of the sequence. Evaluate and then plot it. So let's just quickly run this. 82 milliseconds, and we definitely see a convergence, right? And if you recall, the explicit Euler method converged from below, and the implicit Euler method converges from above, as you can see here, right? And the convergence is still slow. So implicit or explicit doesn't make a difference in the rate of convergence or the speed of convergence, or basically the order of error for both implicit methods of the same family. For example, implicit Euler and explicit Euler, the order of error is the same. So both of the implicit and explicit Euler methods have the same order of error, which is h to the first power. However, implicit or explicit is more about the stability of the solution, right? And then here for test 2, what I have, so test 1 for just creating the sequence for a particular point of x and then looking at the convergence. Test 2 is basically solving the differential equations for many values of x. So from 0 to 50, 1000 points. And I'm comparing the exact solution, y exact, which is the solution is e to the negative t, alright, or e to the negative x for x values. And then y Euler, and which is explicit ones. So this one is explicit. And y Euler implicit, this is the implicit Euler method. The first one is explicit Euler method. And then this is the for loop. For Euler, I get the Euler sequence and then evaluate it at 100. Note that I'm not doing any Richardson acceleration. This is the pure ODE Euler sequence and then evaluate it at 100 terms. Now obviously we expect the error to be large because Euler has a very slow convergence. So we have to go deep into the 1000, 10,000 terms of the sequence to start seeing a good accuracy without any acceleration. So y Euler implicit, get the Euler implicit sequence and then evaluate at 100 terms and then plot it. So let's run this one. And this is what I showed previously. And as you can see, we have this thing because the accuracy, the root finder doesn't go below that 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is like 14 digits of accuracy. Okay, so the root finder doesn't go below this. So I hope you enjoyed this lecture, and please stay tuned, and I'll see you in the next one.